In this video we'll be dealing with VSEPR theory, the theory that tells us how molecules will be shaped based on what we have in the structure around it. The main idea behind VSEPR theory is that electron groups tend to repel each other. You may know from your previous courses that electrons are negatively charged, and what that means is that since electrons have the same charge as other electrons, they will tend to repel each other. What this means is that molecules will take certain shapes as the different groups of electrons try to repel each other. We'll have to talk a little bit more about what it means to have different electron groups. And the way that we're going to break this down is based on atoms that a certain atom is bonded to and lone pairs on that atom. Let's take a very typical case. A molecule where we have a carbon bonded to 4 other things. As was mentioned before, carbon tends to make 4 bonds, and it could be bonded to 4 different atoms. In that case, we would see something as shown here, where we have what's called a tetrahedral shape. You'll see that those 4 atoms that the carbon is bonded to are all equally spaced around the carbon. From above, it looks just like a triangle, but when we rotate it around in space, we see that's kind of got a pyramid shape, which is technically called a tetrahedron. This way, all of the atoms around the carbon are equally spaced. That's only one possibility of what we're going to see. We may also see other cases where we have an atom bonded to only 3 other atoms, as would be shown here. Now in this case, we do have something that really is just a triangle. It's a triangular shape and completely flat. If I were to hold it at the side, you can see that it is completely flat edge on. And this is the shape that helps to space things as evenly as possible, getting those different groups as far away from each other as possible. Now certain molecules may even have a case where we have something bonded to only 2 atoms. Something as is shown here, where it seems to form exactly a straight line. Up to this point, we've only been dealing with cases where we have atoms bonded to a central atom. But we've also seen that lone pairs are going to show up as well, particularly on nitrogen and oxygen atoms for most commonly seen cases in the molecules you're going to be dealing with. So let's take a look at something where we have an atom that is bonded to 3 atoms but also has a lone pair with a large bulb-shaped object here representing that lone pair. It's going to behave in the same kind of way, wanting to repel the other parts. So again, we try to get these 4 groups now evenly spaced around the atom. It could also be possible that we would see 2 lone pairs on that same central atom. Again, the large bulb-shaped groups representing the lone pairs, and then we've got 2 other atoms bonded to that atom as well. One last common case would be the situation where we have 2 atoms bonded to that central atom and only 1 lone pair, as shown here. Now what we'd like to do is to make some sense out of this. If we have a structure where we see how many atoms it's bonded to and how many lone pairs it has, we need to be able to figure out, well, what is that going to look like in 3D based on this VSEPR theory? We've got a whole cluster of things here, but if we look at them a bit more closely, we should see some similarities. For instance, the original carbon that I started with, the one that was bonded to 4 atoms, seems to look similar in shape to this atom here bonded to 3 atoms with lone pair. And then also the situation where we have 2 atoms with 2 lone pairs. Those all seem to be pretty similar to each other. We also have the other cases where we've got the atom with 3 atoms bonded to it, and then the central one bonded to 2 atoms with a lone pair on it. Again, they seem to have that similar kind of flat shape to them, basically shaped like a triangle. And so they seem to be similar as well. And then that last one with just the 2 atoms on it being a bit different from each other. So what we're seeing here is that these groups, which could either be an atom bonded to the central atom, or a lone pair on that central atom, tend to determine the shape here. a good way to characterize the different shapes that we're seeing here is by looking at the different angles that are made by the bonds here. This is referred to as bond angles. So let's look at the bond angles that we've got in this case. In this particular case, we can see that the one that we've got with only 2 atoms on it and no lone pairs, it goes straight across, making a straight line. That's a 180-degree angle. If we look at our flat triangle shape here, which is technically called trigonal planar, the angle that we have here between this outer atom, the central atom, and then going back to another one of the outer atoms, we can mathematically find that that's going to be 120 degrees. Now that's going to be in the strictest case here. If we do have a lone pair, or if the atoms around the central atom are different from each other, there are going to be some differences. So we can just call this approximately 120 degrees to account for that. Now as for the last case here, this is probably the trickiest one to deal with, where we have the 4 atoms or 4 groups, whether they are atoms or lone pairs around the central atom. This is something that, again, we can find through mathematics, but it's a little bit tougher to do. This one comes out to about 109.5 degrees. And again, this is something that is going to vary a little bit, especially when it comes to situations where all of the atoms are not the same when it comes to the ones around the central atom, or if we do have a lone pair or 2 lone pairs on that central atom. As we're building up our models of the atoms, we're generally not as concerned with showing the lone pairs, which might mean that our shapes are going to look a little bit different from what we've got here. For instance, if I look at the case over here where we have 3 groups, 2 atoms and 1 lone pair, if we don't show the lone pair, it would just take on this bent shape. So that would be the way of showing it, where the lone pair is still there and exerting some effect on the shape, but is not being shown specifically. In the case where we have our 4 groups, the one with 1 lone pair and the one with 2 lone pairs, the 1 lone pair would look like this, which is basically a shallow pyramid if you look at it. The central atom is a little bit raised above the other 3 atoms. And again, it's showing this empty space here where the lone pair actually is and it is exerting effects, but just is not shown because we focus more on the atoms themselves. Going over to the case with 2 lone pairs, well, in that case, again, we have what looks like a bent shape. The 2 lone pairs would be coming off to the sides here, completing the shape. But since we are not as concerned with them and don't tend to show them as much, we would focus more on the bent shape formed by those 3 remaining atoms. Doing this kind of assessment for each atom within the molecule can help us to put together an accurate shape for what the molecule will look like as a whole.